Yeah. So we continue. Cat B problem: pulling glasses apart. Right. So put a thin layer of water between two sheets of glass and try to separate them. Investigate the parameters affecting the required force. Okay. So two sheets of glass. Don't have to stretch your imagination. Is this glass, the microscope glass? Okay. Right. So okay. Right. So two sheets of this. I don't know. Mr. Lim said, give each of you two sheets. You all want? Okay, we'll see later. Okay, I don't want you to cut yourself. Okay, so so you may wonder, how do we measure the? So you have these two sheets of microscope glass, right? So you pour a little bit of water on it, okay, right, and then so you stick the, put the two glass sheets together. Then these two will seem to get stuck together, right? Have you experienced this? Yeah. Okay. Right. So your problem, your task is to try to separate them and investigate the parameters affecting the required force. Okay. Now, it seems like this phenomenon is quite well understood. Okay. Right. So the idea is this. First thing that you have to solve. First problem you have to solve is, how do you separate two glass sheets? Okay. So solution. This glass sheets, right? Each of this, you glue each of this to some what do you call it, substrate. Okay, that means substrate is the technical word. Just take a piece of metal, right, and then glue this glass sheet to it. Okay, and then you have the other glass sheet, right? You glue it to the other metal piece. Okay. Right, and then how do you measure force? One idea, I don't know whether it will work or not, okay, is that you place this whole thing on the weighing balance, right, and then you pull. Okay, right, so so roughly the setup, this is actually from one of the research papers, right, so you can put a light source here, okay, and then so these are the two supporting plates, right, so I said metal plates just now, right. You can glue your glass sheet onto this, okay, each of this, like this. Okay, then when you pull it, okay, right, then you will change the shape of this liquid bridge, right, or water bridge between the two glass sheets. Okay, right, and then hopefully your weighing balance is sensitive enough to measure the force. You know what is going on, right? If you pull, the reading is going to increase or decrease? Okay, you decide. Okay, right? And then the idea is that when the shape of this meniscus changes, okay, the force actually will change. Okay, right? So it is not one separating force. You pull and then, I get one value, 10 Newton. That's it. Okay, right? So it's actually dynamic. And since we know quite a bit of the theory, okay. Of course, again, we need the teachers to work through with them, to go through this with them. Okay, right? So that is why right here, separating, okay, be imaginative, separating. Of course, it can be like this. Okay, right? So once you're done and you're tired with this, you can do this. Okay, right? Because if you have a good technique to actually observe this as you pull, right? Of course, you're not going to pull with your hand, right? Or you're going to pull with your hand. Okay, right? So you have to design something that allows you to do this, allows you to do this consistently. Yeah, right? So when we talk about experimental design, okay, observing the phenomenon, fine. Just now, light rings, okay, right? You have water. So during the selection round, just to share, okay, selection round, the schools that did not get selected, right? Most of them, what they did is that, okay, I have water flowing, I shine a laser beam, I see, and that's it. Okay, right? So reporting on the phenomenon is just the 0th step, right? You have to go in and try to do more controlled experiments, right? And ask why are you seeing what you're seeing, okay? And try to make sense of what you're seeing. And when you try to make sense of what you're seeing, that is the first step only. The next step is that, okay, so I have a certain idea of how come, the things are behaving in this way. Then you need to test it, right? Scientific method means you prove not by mathematics, you prove by experimentation. Okay, so you have to design alternative experiments that will support what you believe is going on in the system. Okay, right? So, so yes, you look at I give you some mathematical equations and so on, right? As I said, those things are actually not the most difficult thing. Okay, the more challenging thing is actually to go through the process of asking what you're seeing, why you're seeing this, right? And then come out with ideas of testing, right? That a particular way of understanding what is going on is correct. Okay, right? So the mathematics, as I said, if you find you need anything, okay, you can either ask a teacher or you can, ask my colleagues okay, or ask me okay, right? Then we can work through something, okay, right? We'll see how later, okay, right? So this is roughly how you could set up your experiment, okay. I hope that's clear enough. And theory, yeah, looks like this is it. But as I said, there are actually detailed theories that if you can get hold of the shape of all these meniscus, you can actually have a more elaborate theory. Okay, yeah, right. So the topic for this problem is keywords are capillary bridge. This is the capillary bridge. Capillary bridge forces. Okay, so you can Google and you can find a lot of papers on this. Okay, right. But you have to start working and not keep reading. Right, so I give you a review paper on capillary bridges and capillary bridge forces, and then some of the more recent experiments that were done that actually study the statics and dynamics of capillary bridges. Okay, so you have it here, and then some of the all more recent papers. Okay, right, and then there's one that you can read it yourself. Yep. I'll give you one setup, right? The even more recent paper is that they tube, right? That means they turn this into vertical. Vertical, gravity will have a role to play, right? And then yeah. So notice this problem doesn't say that these two glass sheets must stay horizontal. Yeah, right? Okay. So cat B. Another cat B problem. This time round the guys hair hygrometer. You need hair that is minimum length 20 centimeters. So I don't know how you're going to steal the hair. So minimum 20 cm, right? Okay. So this is one picture that I can find that is simple enough. Okay, simple hygrometer can be built using human hair, right? Investigate its accuracy. Actually, investigate its inaccuracy, right? And response time, right, as a function of relevant parameters. Okay, right? So essentially, what is well known is that human hair stretches in moist air and contracts in dry air. Okay, right? So you can take this as a reference. Okay, the challenging part is actually this part here. Okay, right? This is the part where you know that because as the hair contracts or expand, then it's going to pull onto this thing, right? Which will supposed to give you the indication of the relative humidity. Okay, right? So these are some of the the pictures that I obtained from one of the papers that you have later. Okay, right? These are some of the design for this part. Okay, right? Clear? Now, the first paper that I'll give you, for Cat B, usually, right, try to make it first. Okay, so that's why you realize like the problem number 8, right, the optics on the images, the stringent photography, right. I give you papers that will tell you precisely how you can build one of these optical systems. Okay, so same thing here, right? First paper is on how you can build a hair hygrometer. Okay, right? So after you build one, next thing is actually calibration. Okay, in other words, you need to deal with the scale. What do you mean by 0 relative humidity and 100%, right? Relative humidity. Okay, right? So what you read inside here, okay? I hope, okay, but I need to tell you I hope that you can see that obviously it's going to give a lot of problem. Okay, so what happened here is that the author says, okay, you take your hair, right? Of course you clean it okay, right? So you remove all the dust particles, everything, okay, right? So that part is fine. It comes to calibration. It says this: use a hair dryer. You dry until you feel that you're happy. It is really dry. Okay, that will be 0. Okay, then after that, you take your hair, right, and then you take a wet towel, wrap it. Okay, and you feel you wait until it's long enough. Okay, that is 100. Okay, right. So you know that's really that's going the root of the problem already. That's one thing. Okay, then next comes this. So 0, right? 100, right? Like the centigrade scale, 100 divisions, equal divisions, that will give you the intermediate readings. Okay, assuming that the hair and the relative humidity actually, the properties they correlate linearly. These are all questionable assumptions. Okay, right? So I hope you can read and you are mature enough to see that these are all potential problems. Okay, and these are potential problems that you need to deal with in this problem. Okay, right? So I have one paper that talks about calibration and then various precautions that you have to take note of when you deal with hair hygrometer. Okay, and you have to ask, despite all these problems, how come this hair hygrometer is still very much in use? Okay, right? So it obviously has its advantages and strengths. Okay, right. Another problem which you should be aware of is how we define relative humidity. Okay, right? Why? Because when we talk about accuracy, right? What are you going to do? How do you know how accurate your hygrometer is? You're going to compare with another device that measures relative humidity. So make sure when you tell people, right, you better know that device, what is it measuring? Okay, is it based on the same idea, right? I dry it, okay, because most of these devices, okay, work on basically the same idea. Okay, I dry it, that's 0. Okay, right? I put water until you cannot hold anymore, that's 100. Okay, right? So please find out about the device characteristics, what really they are measuring. And then the other thing is that scientifically, okay, we have a definition for relative humidity, right? Scientifically, relative humidity, right, of air-water mixture is defined as the ratio of partial pressure of water vapor in a mixture to the equilibrium, that's the saturation vapor pressure of water vapor over a flat surface of pure water at a certain temperature. So straight away you can see that, right, relative humidity actually depends on temperature. Okay, right? Because at different temperatures, this saturation water vapor pressure is different. Right? From chemistry, you should have some idea. Okay, right? And so you can see scientifically, right, we have one definition. Practically, we have ways of measuring that quantity. So these are issues that you should explore, right? And then I read this that's why I put in red okay, right here. There's a formula that allows you to work out what is the saturation vapor pressure for a given temperature. Okay, this is a commercial product, a formula behind a commercial product. So you better test it. Okay, especially when it shows 18.678. Wow. Okay, 6.1121. I don't know what those numbers are. Okay, right, so, well, good luck. Okay, Cat B can do it. Yeah, there's a theory by Whipper, which was published in Whipper Museum, the Whipper Museum in Cambridge. This paper is published in 1800s or 1700s. Okay. Right. After that, no one talks about theory of hair hygrometer. But, well, maybe you can find some. Okay. Right. Okay. Right. So, so it seems like so far Cat B is more doable. You agree? Okay, so now I give Cat A doable problem. Okay. Fasten the axis of a wheel to vertical track that has a certain torsional resistance. Right, see figure. Not this one. This one also has. Okay, but not high enough. This one. Okay. Right, twist the track, spin the wheel, and release it. Okay. Right. So I say again. Spin the wheel. You're not going to do this, right? Yeah. No one is going to tell me you spin by hand. Right? So how do you spin the wheel? You need something to rotate and put the thing on it. Yeah. Okay. Right. And then release it. Okay. Investigate the dynamics. Right. I added my own words. That means the time evolution. How does the thing evolve over time? Okay. Of this system. So dynamics, right? Time evolution means what you have to take into account the forces, the torques acting on the system. Okay. Right. And then use Newton's second law. Okay, right? This problem, what do you think is the headache? No lah, torsion is easy. The headache is the frictional torques. Okay, the possibly velocity dependent dissipative forces. Okay, right? So so this one. Okay, take note. Now I'm going to show you this video, and I see whether you are good enough for IYPT. I thought this is actually related. It's not the problem, but it's related.